So this is section 1.3. So we're going to talk about how to evaluate a limit. So we've already kind of discussed looking at the graph, creating a table, direct substitution, and then we're going to have to simplify functions until we can actually do some direct substitution. So before we can do that, we have to know our properties. So when I'm talking about properties, these are all properties of limits. So the first one is talking about the limit as x goes to c of b is equal to b. So what does that mean? So if you have to think about this, your b is actually your function. So think of it as just being like f of x or y equals b. So let's think of it as y equals b. So you're actually looking at a horizontal line. So my picture is not great. So if we think of this horizontal line and x equals c, so we're going to put c over here and it doesn't matter where c is. So if we are actually looking at that from the left and from the right, remember we said in order for a limit to exist, they have to go to the same y value. So because it's a horizontal line, that value is always going to be b. So b is where that horizontal line is located. Now, looking at the next one, when you're talking about the limit as x goes to c of x to the n. So this is any polynomial function. So if you're thinking about your direct substitution, you're really just plugging c in for your n. And so that gives you your limit. Same thing works with radicals, because remember radicals are the same as just a power. It's a fractional power, but it works the same. So we can think of this as x to the 1 over n. And then again, you're doing some direct substitution and you get the nth root of c or c to the 1 over n. Trig functions. So again, direct substitution. So if you're doing the limit as x goes to c of the sine of c, or sine of x, you're going to replace the x with the c and that gives you sine of c. Rational functions work the same way, as well as composite functions. Notice though with composite functions that we can pull that function out and put the limit on the inside. So that's something that's a little bit different than the previous ones. So let's look at an example. What if I gave you that the limit as x goes to c of f of x is 7 and the limit as x goes to c of g of x is 3? So if I were to evaluate these individually, if I'm looking at A, I have the limit as x goes to c of 3 times f of x. So really what you can do is with that constant, you're going to pull that out front. So I could rewrite this as 3 times the limit as x goes to c of f of x. Well, we know what the limit as x goes to 3 of f of x is. So we're just going to take 3 times 7, which is going to give me my limit is 21. Now, technically, we should have some brackets probably here. So when we have the limit of these two functions that are added together, you could actually rewrite that as two separate limits. I'm going to say the limit as x goes to c of f of x plus the limit as x goes to c of g of x. What that allows you to do then, you can evaluate. So what are you doing? You are actually replacing, we know the limit as x goes to c of f of x is 7. So we're going to say 7 plus 3, and that's going to give us 10. The same works with multiplication and division. So I don't have a whole lot of room here, but if you're thinking in terms of the same thing, we're going to say the limit as x goes to c of f of x times the limit as the limit as x goes to c of g of x. So again, you're pulling them apart. So when you pull those apart, that gives you these two pieces just multiplied together. So then this would be 3 times 7, which is also 21. Now, the next one is division. Idea is still the same. We're taking the limit as x goes to c of f of x and dividing it by the limit as x goes to c of g of x. So you're dividing the two functions. So we're going to have 7/3. This is our root that we did earlier. So if we're doing that, we can say that this is going to be the limit of g of c. So this is g to the 1/2 power. So then this would be the limit if we rewrote this of g of x, which is just our function, to the, not 1/3, how about 1/2 power? So we can actually just replace that. So that would actually be 3 to the 1/2 power. The last one, as x goes to c of f of x to the 3rd. Again, these are kind of like our composites. So we are going to put that limit on the inside. So it would be like saying the limit as x goes to c of f of x to the 3rd power. So we're thinking this as a composite function. So for instance, g of x is inside of this square root. That's why we're putting that limit. So it's all of this to the 1/2 power. That's what it's allowing us to do this. So we have 7 to the 3rd. So here is an example then of all of your properties. Now, again, we need to know our techniques for evaluating limits. So one of our techniques is to cancel common factors. So we have to be able to factor. Again, be very careful with limits. Make sure you're using correct notation every time. You have to write the limit as x goes to 4. So we're going to factor the numerator. So when we factor this, we would have x minus 4 and x plus 3. We're going to factor the denominator as well. And what we see is they have a common factor. If we were to do direct substitution right now, we'd get 0 in our denominator. So we can't necessarily do that because really our function, this entire function is undefined at 4. We can't do that. But we can find the limit because remember the limit, the actual value at that point doesn't have to exist. We need to know that it's going to, if we look at the graph, it's going to the same y value from both the left and the right. So when we do this, we will cancel those common factors and then do our direct substitution. So we're going to plug 4 in here. So we'd have 4 plus 3 over 2, which is going to give us a 7/2 would be our limit. So again, that does not mean that that function at 4 is equal to that. That means the limit of that function as x goes to 4. So remember that you're coming from both sides. So from the left and from the right, it is approaching 7/2. Again, here's another common factor type question. Again, make sure that your notation is good. Always write the limit. So we have x plus 7 and x minus 7. And then denominator, we're going to have x minus 7 and x minus 3. Again, if we did direct substitution, we'd get 0 in the denominator. We can't have 0 in the denominator, so it is undefined at 7. But when we factor, we can cancel those like terms. So again, direct substitution now is going to give us 14 over 4 or 7/2. So again, it does have a limit, but the value of that function at 7 is undefined. So another technique is to rationalize the numerator. This is opposite of everything that you've done in algebra. You always rationalize the denominator, but in calculus, usually you rationalize the numerator. So if we look at this, when we rationalize, we're going to multiply by the conjugate. So it's the conjugate of the top. So we're going to multiply by the square root of x plus 2 plus 2. So conjugate means the two pieces are the same, but the signs in the middle are different. Whatever you multiply on the top, you have to multiply by the same thing in the denominator. Now, when you do this, you will distribute out the numerator, but you will not do the denominator. So you need to leave it the same. So what we're going to have, again, notation, limit as x goes to 2. When we distribute here, that would give us the square roots will cancel. So we're going to have x plus 2, and then plus 2 square root of x plus 2, minus 2 square root of x plus 2, and minus a 4. Again, in our denominator, we are not going to multiply these out. We are going to leave them exactly the same. But what you will notice is in the numerator, those two middle terms will cancel. We can combine our like terms in the numerator. And that's going to give me an x minus 2 over x minus 2 times the square root of x plus 2 plus 2. So again, just like before, we have a common term in the top and the bottom, because again, we can't do our direct substitution here until we cancel that like terms. That leaves you a 1 in the numerator, and now I can do my direct substitution. So when I plug in my 2, I would have the square root of 4 plus 2. Well, we know the square root of 4 is 2, so I would have 1/4. So let's try another. So again, we have to multiply by the conjugate. This one's written a little bit different, but very similar. We can't do direct substitution here because if you plug in 0 for your x, we do get 0 in the denominator. Our conjugate, remember, you leave the terms the same and change the sign in the middle. So this time it's a plus. So we'd have 3 plus the square root of x plus 9. Again, whatever you multiply on the top, you must multiply on the bottom or in the denominator. Distribute the top. When we distribute, we're going to have 9. Again, because they're conjugates, those middle terms will cancel. I'm going to put minus. This is where you have to be very careful. When you multiply these two, you have to put parentheses. If you don't, it's not going to work out correctly. So we'd have x times 3 plus the square root of x plus 9. Again, I'm not multiplying the denominator out. I do need to distribute. When I distribute, notice I'm keeping my notation. I would have, and I'm going to write it above so I'm not wasting a bunch of space, my 9 and my negative 9 will cancel, so I have negative x over x times 3 plus the square root of x plus 9. What happens here, again, we have like terms. My x's will cancel. That leaves me with a negative 1 in the numerator. Now I can do my direct substitution. So I'd have negative 1 over 3 plus 0 plus 9 is 9. So square root of 9 is 3. So I'd have a negative 1/6. Again, that gives you two examples of rationalizing that numerator. The next technique that we are going to do is to multiply by a common denominator. So what you'll see with these, you'll see a fractions within fractions. Again, direct substitution won't work. Our denominator would be 0. So our common denominator here is we look at our two denominators. We have an x and we have x plus 1. So your common denominator is x times x plus 1. So what you're doing, again, is you're multiplying that on the numerator and the denominator. So we are going to distribute that through our numerator. We are not multiplying, again, our denominator out. We're going to say the limit as x goes to 1. When you distribute x times x plus 1 times 2 over x, the x's will cancel. We're left with 2 times x plus 1. Distribute on the second, the x plus 1s will cancel, so we have minus 4x. Again, I'm going to leave that denominator the same. I'm not going to multiply that out. We do have to simplify our numerator. In this case, it's going to give us a 2x plus 2 minus 4x. I am just writing it there so that I can kind of skip a step. If you need to write that out, write it out. So that's going to give me a negative 2x plus 2 over, x times x plus 1, x minus 1. And you'll notice here we've kind of got a problem because we still can't cancel out, and we really have to cancel out that x minus 1 term. So we have to think about what we can do with that numerator. So what we can do is factor out a, and I'm going to write it on this side here. We have the limit as x goes to 1. We're going to factor out a negative 2. When we factor out that negative 2, that's going to leave us with an x minus 1. And that's going to be helpful because we can cancel that term out that's causing us our issue. So if we now cancel out that term. That allows us to do our direct substitution. So we're plugging in 1. So we'd have negative 2 in the numerator, 1 times 2 in the denominator, and when we evaluate that, we get a negative 1. So again, we have 3 different techniques that we've talked about. We have where we factor and cancel like terms. We have multiplying by a conjugate and finding that common denominator. Now, it gets a little more complicated when we get into our trig functions, because you don't see this as multiplying by a common denominator. But if you think back to what we've learned in trig, we have the limit as x goes to pi, but we can rewrite secant. We can rewrite secant as 1 over the cosine of x. When we do that, now we have our fraction within a fraction. So we are going to multiply at the top and the bottom by our denominator. So we're going to multiply by cosine of x. Again, when we do this, we're going to distribute out in the top but not in the bottom. So we have the limit as x goes to pi. When we distribute that, we have 1 plus the cosine of x. And you'll see how this is kind of nice. We have cosine x plus 1 times the cosine of x. Now, our numerator and denominator, we can cancel those like terms. That leaves us with a 1 in the top. So when we evaluate, we get 1 over the cosine of pi. So now you really have to think back, okay, what is the cosine of pi? Well, let's think back to our unit circle. We know that this is 0, pi over 2, pi, 3 pi over 2, and 2 pi. So pi is over here, and remember we had a coordinate here. And our coordinate here is negative 1, 0. What we have to remember is that a cosine is our x value and sine is our y value. Therefore, the cosine of pi would be negative 1, and we'd have 1 over negative 1, which gives us our limit would be negative 1. So again, you need to refresh your memory, not only on your unit circle, but also on your hand trick. So we have what we call the squeeze theorem. So we're saying in this, if we have 3 functions and it's saying one function's less than the next function's less than another function. So let's talk about this in general. So let's say we have this here. We're going to label this h of x. So this is one function. We have another function, we'll use it red, is here. And we have a third function that's g of x. We'll do it blue. So let's say it's up here. So we have these 3 functions, and they follow this rule where one is greater than another, so on and so forth. And it says for all open x in an interval containing c. So what they're saying is you're looking at a specific interval. So like a specific place. So think of it as I'm looking here. I'm looking in between those 2 brackets. And really I should use parentheses since we're saying they are open. That means that it is not including those endpoints. We're saying there's some x value c that lies somewhere in between there. If that's the case, and so this was just to kind of give you a visual, and the limit as x goes to c of h of x, which is our bottom piece here, is L, and the limit as x goes to c of g of x, which is our top function, is L. So if these 2 limits, if these 2 y values, remember that a limit is a y value, is L on the top function and the bottom function, then the middle function also has to be that. So that's where our squeeze theorem, squeezing it together. Think of these purple and blue lines kind of squeezing on top of that red line. And so that's what our squeeze theorem is saying. So we have some special trig limits. And so when you're looking at these are things for right now. You really just need to memorize. So you need to know that the limit as x goes to 0 of sine x over x is 1. But you also need to know, and this one is not necessarily here, the limit as x goes to 0 of x over sine of x is also 1. So these are 2 that could be interchangeable. But then you also need to know the next one. The limit as x goes to 0 of 1 minus cosine of x over x is 0. And later on, we will learn what's called L'Hopital's rule, which will show why these things work. But for right now, we just need to be able to know them and use them. So this is the first one that we are going to do. So if you think about this, it kind of looks similar to that, the sine one. However, we have a 2 here. So what we need to do is let's think about it as using some properties. So I really need whatever is here to match what's on the bottom. And right now it doesn't. So I really need a 2 on the bottom. But knowing our properties, if we multiply the bottom, we must multiply the top. So I'm going to put 2 on the top and 2 on the bottom. What we can do, and these are our properties of limits, since I have a 2 on the outside, or out in front of the sign, I can actually move, because it's a constant, out in front of the limit. So then I have the sine of 2x over 2x. And just like I said earlier, I need these things to match. And as soon as they match, then this is really equivalent to saying, since they're the same, just like if they were x and x or 5x and 5x, the limit of that is 1. So that answer would be 2. And that would work in any case. So for instance, if I had a 5x there, I would need a 5 on the bottom, and I could put a 5 out in front of the limit. So make sure that you are writing all the steps when you do something like this. You can't just skip to the answer and add a 2. So be careful when you are writing that out. For some reason, it copied the same things. So let's look at another one here. So it's evaluate the following limit. Now it doesn't look like it fits anything that we have done so far. But what we can think of is going back to trig. We know that tangent is sine over cosine. So we're going to rewrite this. And then now we have a fraction over fraction. Now, we don't want a fraction over a fraction, so what I'm going to do is multiply by the reciprocal. So when I do that, the denominator cancels. That leaves me with the limit as x goes to 0. And I could write this as sine of x over x times the cosine of x. Well, it doesn't look very helpful. So what I'm going to do is I want to make it look like those properties above. So I'm going to say the limit as x goes to 0 of the sine x over x times the cosine of x. So technically it's the same thing, it's just rewritten. Now it kind of looks like one of our properties, but now we have this product. So we are going to use that rule that we had earlier. So we're going to say the limit as x goes to 0 of sine x over x times the limit as x goes to 0 of cosine of x. So we know this first part is equivalent to 1, but then it's times the limit as the cosine of x goes to cosine or 0. So we'd really have the cosine of 0. So we need to think about that. What is the cosine of 0? Again, going back to our unit circle, we have 1, 0. Cosine is your x value, so cosine of 0 is 1. So this is equivalent to 1 times 1, which is 1. Again, something very similar. We have cosecant. The cosecant, remember, is 1 over the sine. So we're going to say the limit as x goes to 0 of x times 1 over the sine of x. So you can see this pretty quickly, that this is really x over sine of x, which was the additional 1 that I had written earlier, which is equivalent to 1.